Good afternoon, math teachers and educators. It looks like it is officially 4 o'clock Eastern Time, 3 o'clock Central, and we're going to go ahead and get started with this afternoon's webinar with Professor Eric Milou. We're pretty excited to have him joining us this evening. So thank you again for your time. We know that your time is very busy as well, so thank you for dropping in. We're going to go ahead and get started. And just so that you know, a couple of house cleaning type of things that we'll go over is our phone lines are muted. So you have a couple of options, and we highly encourage you to chat in questions. So what I would like you to do is look over to the right-hand side of your screen on your GoToWebinar panel, control panel. You're going to see a couple of different options there. One will be chat or questions. Please feel free to chat in any questions that you might have, and we'll be relaying them to Eric as we're going along. So please feel free to do that. So again, if you want to get that control panel out of your way, there's also going to be a little orange button up there with a white arrow. You can push that. It will minimize that screen so you can have a larger real estate as he's presenting. So as we're getting started, I'm going to go ahead and flip our screen here. This afternoon, we're going to be talking about how it is that we can engage high school students through authentic mathematical modeling. And as we're getting started here with Eric. There we go. We got a little bit of a delay. Sorry about that. Let me go ahead and introduce Eric as we're getting started here. Eric Milou is a professor in the Department of Mathematics at Rowan University in Glassboro, New Jersey. Eric teaches pre-service teachers and works with in-service teachers and is primarily interested in balancing concept development with skill proficiency. He was part of the 9-member NCTM feedback advisory team that responded to and met with the Council of Chief State School Officers and National Governors Association representatives during the development of various drafts of the Common Core state standards. Eric is the author of Teaching Mathematics to Middle School Students, published by Allen and Bacon, and he is a member of the authorship team for Envision Math 2.0, grades 6 through 8, and our new Envision AGA. So we're pretty excited, obviously, to have Eric joining us this evening. So without further ado, we're going to change controls over here to Eric, and he's going to get us started.
Thank you very much, Tanya. As Tanya said, my name is Eric Milou. I teach mathematics at Rowan University, and Rowan University is in Glassboro, New Jersey, which is right outside of Philadelphia, about 10 miles outside of Philadelphia. If you're not familiar with that area at all, about 25 years ago, a man by the name of Henry Rowan donated $100 million to what was then Glassboro State College. And shortly thereafter, Glassboro State College became Rowan University. And that's how the university became. I've been there for 20 years now, teaching mathematics to pre-service and doing in-service professional development. And so today's webinar is engaging high school students through authentic mathematical modeling. So this is typical math problem solving in typical math textbooks that we see on the market today. A problem like this: a water tank is in form of a regular octagonal prism, and the base octagon has side length 11 and 9/10 centimeters, and the lateral edge is 36 centimeters. And then you get a host of questions like, what's the surface area of the base? What's the volume of the tank? And if you pour water into the tank at a rate 1.8 ounces per second, how long will it take you to fill the tank? And my colleague and friend Dan Myers says, and I agree, is problems like this just plainly suck. They don't motivate, they don't engage, and they're clearly not authentic. And if you ever get a time down at the bottom of this slide, it's Dan Myers' TED Talk. It's about a 15-minute TED Talk. It's worth 15 minutes of your time. It's called Math Class Needs a Makeover. And Dan will explain in more detail about how we can make over the whole class. In this webinar, we're just going to talk about problem solving and in particular mathematical modeling. So how do we just make over this problem? Why does this problem not be very authentic? It's very fake. All the numbers are given, you got a terrible line art here, and you got so many steps that kids are intimidated. So the first step to really make this more authentic is take away some of the information to stop the intimidation of our students. Let's just take away everything, the numbers, most of the words, and just leave this. A water tank, how long will it take you to fill the tank? And if we start right there, I call this problem has now become low floor, high ceiling. And what I mean by low floor and high ceiling is it's low in the sense that every single kid can enter the problem right now and give me a guess. Every single kid can ask, well, I need to know more information. There's other things I need to know to help me solve this. And we can have a discussion about what those things are we need to know. In other words, is the height of the water tower important? Is the color of the valve important? And these are discussions about the variables in the problem that are a very low floor, and every single kid can enter the conversation. This is important to me, that we have problem solving that's authentic, that we can start and invite all kids to the conversation. Dan will further talk about how to make this authentic though, because right now it's still just line art on the page. And really the next step to make it authentic is to have a real water tank like we see right here. Now it's an authentic water tank that I have in my backyard, and I have a hose pictured also. Now I invite you in the conversation and ask you the same question. A water tank is pictured. How long will it take to fill this tank? And at this point, I stop the conversation and ask every kid to think about this for about a minute and give me a guess. If you guys all on the webinar right now think about it for just about a few seconds and then type in your answer in either the question or the chat feature. I'm not sure which one works best. And maybe Tanya can help me there. And give me a guess of how long you think it will take to fill up this water tank with that regular green garden hose in the background. Go ahead and make your guess.
Great. Yes. Go ahead and please just chat that in. Okay, so I'm going to just start calling out some things, Eric, that I'm seeing. I
Just wait
see
a couple more,
couple more
just wait a
seconds.
couple more
Okay,
seconds
sure.
for everybody to guess. Because the one thing I don't like to happen in a classroom is if someone hasn't made a guess yet and they hear someone else's guess, they're influenced by it. So I want every kid to get that 1 minute think time before we start shouting out guesses, because then you're influenced by other people's guesses. So when think time is over, I can't see the chat for some reason, so Tanya's going to relay what your guesses are. Tanya?
Are you ready?
Yep.
Okay. I have 30 minutes, 5 minutes, 2.75 minutes, 12 minutes, and 11 minutes.
So quite a range with just a few adults on this call from, what was the low, 2?
2.75.
And what was the high?
30.
30. I believe fundamentally, if we approach modeling like this, I have sucked you in. I have baited the hook. I have brought you into the conversation. And I believe most of you would like to know the answer right now. Most of you would like to continue with the problem and figure out the answer because you're invested in the problem by your guess. Even though some guesses might be outlandish, everybody wants to be right because we're human. And at this point, we do persevere because you're intrigued by it. What many people will call, this is Act 1 of a mathematical model and situation, where I gave you an authentic, real situation and asked you to make a guess. Act 2, many people will call, is what are the variables? What is the math we need to solve this? What do you need to help solve this. And at this point, I want kids to brainstorm what's important, what are the numbers and variables that I need to solve this. Can't do this very well in a digital webinar, so I just have to give them to you. But at this point, I really want kids asking me what are the variables. So I think most of you know what the variables are, okay? Is that in this particular case, you need to know what? Maybe you need to know the length of the top. It looks like the diameter because it looks like there's a circle across there, but technically this lid is an octagon. You also might need to know what? The height of the water tank. And what about the length of the side of the octagon? And the last thing you definitely need to know is the water rate. And I tend to not give this as a rate. I tend to show them a short video and they have to figure out the rate. Just watch this. Oops, it's not what I wanted to show you. So that's actually Dan up at the top there filling a measuring cup. And he's filling up 16 ounces. And 16 ounces took 8 46 seconds. So given that information, given this, 29 9/10, and the height is 36 1/2, and the side length of the octagon is 12 4/10, and now you can figure out the flow rate. Now you can do the math. And again, it's hard to do this math on the webinar right now. But if you worked out that math, and I gave you 5 to 10 minutes to work out that math, the first thing you might do is go look up the formula for how to figure out the area of an octagon. And you might figure out how to find that area on Google. And then you might time that area by the height, and that will give you the volume. But then that volume would be in cubic centimeters. And you then have to think, well, wait a second. The flow rate's in ounces. So now I have to go figure out the conversion from cubic centimeters to ounces, and then set up a proportion to find the amount of time it would take to fill up this entire volume. Now that's true, authentic mathematical modeling. And I want you to think about just how different that is from starting here, where it's totally inauthentic. And it doesn't engage and it doesn't motivate our students. Take away the numbers, take away the ABC. At least try to start here. We can be more authentic here. And then after estimation and guesses are made, we can start providing information for kids to help them solve it. Once they solve it, I often have kids present their solutions, and then Act 3 is the final act. How long did it actually take? And this is the video of how long it actually took to fill up the water tank. And it was just over 8 minutes, 8 minutes and 11 seconds. If you did this math out, you would come up with really close to 8 minutes and 11 seconds. Some of my students who have worked it out come up with 8 minutes and 4 and 8 minutes and 5 seconds. And then we have a conversation of why the math comes out at 8.4 or 8.5, but actually it comes out to 8.11. And of course that conversation is about error. And there's a good conversation about where is the error on your rounding, on your formula. And that's authentic math modeling in the spirit of a 3-act lesson, often the term coined by Dan Meyer. So I want to show you some more of these and take them a little slower for you guys. But just to recap, the Common Core calls modeling an important standard. And it has these 5 aspects that students, not teachers, students must identify variables. Students must formulate the model. Students then perform operations on the model. Students interpret the results, and students validate the conclusions. Those 5 steps are essential to mathematical modeling. But often what happens in textbooks, on the left-hand side of this chart, is the model is already given to kids. The variables are already given, and the model has no error. It's not authentic if the variables in the model is given. And we want to move more to the right, more authentic, where we start with picture or video with very little text. Students have to find the variables. Students have to create the model with some teacher support. And then students have to validate their conclusions and reflect on where the error could be. Much more authentic on the right-hand side. And I like to think how we can move from a typical situation to more authentic on the right-hand side, as presented in the previous problem. And I'm going to try to do 2 or 3 more with you during this webinar. So here's the next one. I want to review the first act. The first act is a visual. It's a photo or a video intended to hook you. And it leads to a guess. It leads to an estimate, a guess, a hypothesis, like you just made on the water tank. It's also crucial that students are involved in defining what the question is in the first place. So here is one. This is by Andrew Stadell. Andrew is a middle school teacher out in the Los Angeles suburban area. And it starts like this. So Andrew is stacking cups in front of his front door. And that's it. And I turn to my kids, and I want the kids to help define the question. And I'll tell you, doing this with 9th graders in an Algebra 1 class is an Algebra 1 lesson, believe it or not. There's many questions they have at this point. A lot of kids focus on what is this 40 right here. And that's irrelevant, but they do ask good questions like that. They see a number in the problem, so of course the number must have something to do with the problem. It doesn't. But they ask, well, maybe how many cups does it take to stack to reach the 40? Other kids say, how many cups does it take to stack to reach his head? Other kids say, how fast can he stack them? And then other kids say, how many cups will it take for him to stack all the way to the top inside lip of the door? And that's actually the question. We want to find one stack all the way to the top inside lip of that door is our question today. So students ask a lot of different questions. I will focus on the question that is going to be part of the lesson today, that one stack all the way to the top inside lip of the door. And now I want the guesses. So go ahead again and type your guesses in, and I'll have Tanya relay them to me. One stack all the way to the top inside of the door. We'll give it about 10 more seconds, Tanya, and then hopefully you can relay them, some of their guesses to me.
Okay. I have 156, 130, 200, 58, 117.
Again, those guesses are all over the place. And I think one person has done this before. There's always that one person who's done this before and knows the right answer, I think. But again, those guesses are all over the place in the 20s and 100 or 200 in there. And we want to discuss, well, how did you make your guess? Did you really understand the problem? When you come up with a small number, how do you make your guess? What benchmark did you use? Is there about 15 cups here? Do you want to see the video again before you make your guess? And we have those discussions with kids. But I think it's crucial that they are invested in the modeling by first making a guess, and then we moved to what many people call is Act 2 of the problem. And Act 2 of the problem is we begin the modeling. We ask kids, what more information do you need to answer our question? We ask kids, how do you get it? We ask kids to gather tools and information and resources to answer the question. And only once students decide what information they need will the teacher give it to them. The teacher has to be a resource here. The teacher can't say, you need X, Y, and Z. Students have to ask, what are the important variables here? What do I need to solve this problem? Do I need the volume of the cup? That has to be a discussion, is what are the important variables? Of course, I think everybody on this call understands what the variables are, but I want you to be a resource and have this discussion with your students about what are the variables. I think, again, all you know the variables are you need the height of the cup, you need the height of a lip, and you need the height of the door. And only once kids have asked and we have discussed this will I provide this information. And then I give them 15 minutes or so to work on it. 15 minutes to see if they can figure out exactly how many cups there are. There's many different solution methods. I think I might just give you a minute or two to see if you can work out a solution method right now. Go ahead and try. You notice again there's a little piece missing where I want kids to again gather resources and tools on Google or whatever, because some measurements are in centimeters and some are in inches. I want kids to realize there's multiple approaches here. Some kids realize this is a linear function. Other kids don't use any algebra whatsoever and will use some numerical approaches here. One of my favorite approaches from a student is to take the door height, convert it to centimeters, and subtract the full cup, 9.1. Whatever that result is, the kid then divides by 1.3. And then the kid says to me, I need to add a cup back because I subtracted off a whole cup. And I think that's a wonderful approach without any algebra whatsoever. An algebraic approach might look like this, where you realize that I have a linear function here. That's 1.3x plus 7.8. Many kids will write 1.3x plus 9.1, and we have to discuss why that might not be correct. And I probably should do a better job on this slide of labeling my variables. My x variable is the number of cups. So if x is 1, I got 1.3 times 1 plus 7.8, which gives me the height of 1 cup, which is 9.1. And then if I do the algebra here, first the conversion, then the substitution, and then the algebra, I wind up with 156 and 9/10 of a cup. Then the discussion gets really interesting in the class. Should it be 156 cups or should it be 157 cups? Which is correct? And we have a really interesting debate of whether or not Andrew can squish another cup up top there, or can he not? We end with, again, what is commonly Act 3. It confirms the answer, but it's not an answer key. It requires a conversation about error. What did our model not include that it should have? What did our model include that it shouldn't have? Why was our answer close but not exact? And that discussion is paramount to mathematical modeling in a successful classroom. We then show the answer in the final act here. I kind of call it the reveal. And here's Andrew stacking all the cups. It's an ugly sweater, by the way, Andrew. And our algebraic solution said 156 and 9/10. what does Andrew actually get when he's authentically doing it? $155. He's got two more in his hand, 156, and there's a lot of tension in the class. How about that last one, Andrew? How about that 157? You gonna try it? Doesn't even try it. 156. Sometimes there's applause, sometimes there's booing, but there's some real interest there on the algebra coming out with 156 and 9/10, and Andrew coming out with 156. What about the sources of error here? Is the final conversation. But I love the authenticity of the modeling process here. That the variables are not given, the model is not given. These are things that students have to do. Let me show you another one. This one is by Michael Fenton. Michael wrote this lesson called Charge. So charge starts like this. It doesn't start with a video at all. It just starts with this picture. And that's it. Now when I ask kids to look at this picture and tell me what questions they have a lot of questions. Some of the obvious ones are, how much time will it be until my phone dies? Obviously a good question. Other questions that kids ask are like, why in the world would you have Sprint? And other kids ask all kind of other crazy questions about battery life and time, and alarm, and is this AM or PM? The question we're going to focus on is similar to how much battery life you have left, but it's kind of the opposite. And so today's question will be, how much time will it take to charge your phone, assuming you plug it in right now and don't use it? And that's a very interesting question to have kids make an estimation about, because they will ask other questions, like what kind of charger? Are you on airplane mode while you're charging? They ask all kinds of questions because they have real experiences with charging their phone. Some of those questions I can't answer, and I'll just say make a guess. So plug in your phone right now. You won't use it. How long will it take to charge? Go ahead and take 1 minute and put your guesses in. It's 9:02 p.m. pretend. I'm plugging in my phone right now. How long will it take to charge? I'll give you a minute, and then Tanya can read out some guesses. And again, kids want to ask so many other things here. Kids want to ask about all kind of possibilities when you're charging your phone, which is just some interesting questions that they really have here. Can't answer those, but there's some really good debate about what variables do affect phone charging. Tanya, give it about 10 more seconds, and then if you could read out some guesses for me.
Okay. We have an hour, 60 minutes, 2.5 hours, 25 minutes, and 90 minutes.
A lot of different guesses there, and most of those guesses are built on your own experiences with your phone and your charger, by the way. But we got guesses under a half hour, and we got guesses around 2 hours. I again believe you're hooked into my lesson because I made you first make an estimate, and you're human. You want to be right. So, Act 2, what are the variables here? So I will start Act 2 by giving kids this slide, and I'll ask them how they can now figure this out. So I gave them for what? I always say for what to my kids. I would like them to say these are 4 data points. I don't always get that, by the way. These are 4 ordered pairs. And then what are you going to do with those 4 ordered pairs? You're going to graph them, and you're going to try to find the function that fits these 4 ordered pairs. And then try to figure out when does that function get to 100% charged. So we have to really define our variables, what's our independent variable, what's our dependent variable. And we have some really good authentic math modeling here. These are actual times and charges by Michael Fenton's cell phone. So we can see our x variable is actually time since 902. And a lot of kids just want to make the x variable 902, 910, 914, 926. And in fact, the x variable is the time since I plugged in the phone. And the y variable is the percent charge. So the first data point is 0, 5. And a lot of people want to make it 2, 5, and it's a really good discussion. The second data point is what? The second data point, this is 8 minutes since it's been plugged in. So the second data point is 8, 14. After 8 minutes, it's 14% charged. And the third data point after 12 minutes, it's 19% charged. And the last data point after 24 minutes, it's 33% charged. And from there, kids use a lot of different things that they have learned. It really matters if you're in Algebra 1 class or Algebra 2 class, which functions have you studied to this point. I like to turn the problem now into technology and use Desmos. I like to just come out here and graph them into a function. I define my variables, y being the battery charge as a percentage, and x being the number of minutes since 902, and I graph my data. And there's my data graph there. And let me just make it a little bit thicker there for you. And when looking and analyzing that data points, remember here's the data points, it certainly looks like this is perfectly linear. Certainly looks that way. My green line is y equals 100, it's 100% charged. And I want to find out when I get to 100% charged. Some kids start calculating slopes, or other kids just experiment with their own equation. Most kids just start with y equals x. Y equals x is not too bad after all, by the way. Okay? But we know the intercept should be 5, so why don't we do y equals x plus 5? That's not too bad whatsoever. I don't like green there. I'm going to change it to red just because the y equals 100 line is green. And maybe that slope's a little bigger than 1, so most kids then go to 2. Oh, that's way too big. And then they start playing around with the slope. And this is exactly what you want kids to do when you're mathematically modeling. Well, 1.2 looks pretty good. What about 1.1? No, 1.2 looked better. What about 1.15? And you really got a lot of authentic mathematical modeling with real data from Michael Fenton's cell phone. If we agree that this is a really good model, we can click here and see that at 100% it took 82.6 minutes, or about 82 or 83 minutes, about an hour and 22 or 23 minutes is what it took. And we're done. No, we're not. We're not done, boys and girls. We made an assumption here. I turn to my kids. We made an assumption. We assumed that this data was linear. And is that assumption 100% correct? We're not really sure until we actually collected all of the data. So I will now show you all of the data. I'm going to turn off those first 4 points and show you all of the data. So here is all of the data, and I'm going to actually just play it for you. And oh my gosh, what happened is that it was linear for only about 80% of the time. But for the last 20%, it really was not linear at all. It really took a long time to charge that last 20%. a really long time. That's true about most cell phones, by the way. Put that back on, you see it's linear for a lot of the time. But for that last 20%, boy, does it take a long, long time. Okay? And that's intriguing that this function is not linear the whole time. To show you the actual amount of time it actually took him to 11:22 to charge his phone. So it took 2 hours and 20 minutes. If you look back at the graph here, this point is about 2 hours and 20 minutes to get to 100%. That's amazing. I often, for homework, ask kids, do it yourself. Plug in your phone, take screenshots about every 3 to 5 minutes, and graph it. Will it be linear the whole time, or will it work like Michael Fenton's cell phone, where it's linear for a while and then nonlinear? It's a wonderful, authentic mathematical model and task, and I think we need to do more tasks like that in our classrooms. I have one more for you today, and this final one is called Penny Circle. This is by Dan Meyer. It starts like this. So the question is pretty obvious. Every kid jumps up in a classroom and says, I know what the question is. How many pennies are going to fit in this big circle? And that's true. That's the question. How many pennies are going to fit in that big circle? But the guesses, the estimation here is quite intriguing because there's going to be a wide range. I'm going to give you a minute and put your guesses in again. I'm going to play the video again for you, though. How many pennies will fit in that large circle? Here's the small circle. How many pennies will fit in this large circle? Many kids want to see the video several times, and that's not a bad thing at all. I love to show it several times if that's going to help them be more engaged in the lesson. I'll give you one more video, one more shot, and then put your guess in. All right, so Tanya, do we have guesses?
We have one.
Oh, only one person brave enough on this one. What was the one guess we have?
We have 1,800.
1,800. Wow. Wow. Anybody else brave enough? No one else brave enough, Tanya?
Doesn't look like it. Oh, we got a couple. Yes.
Wow.
All right, we got 750. We got
Uh-huh.
3,700.
Wow. All over the place with just 3 guesses. Tanya, what's your guess?
I'm going to say 2,000.
2,000 for Tanya. Again, I like it done privately so you're not influenced by other people's guesses. I like to give every kid a Post-it note. I like to give them 1 minute. They put their answer on the Post-it note and they bring their Post-it note up to the board. I don't make them put their name on it. I just want to have everybody invested. They also write their answer on a piece of paper at their desk. And at the end of the 3rd act, I always give out a prize to the kid who's the closest. So what are the variables here? What's the act 2? What do you need to solve it? Oops, let me not play the video again. So there's 3 different handouts here, 3 different ways to approach it. One, you just give out this and a ruler and pennies. Or you give out this and a ruler. Or you give out this. Most teachers move to this 3rd handout, where there's no pennies given out, there's no rulers given out. I'm basically giving you 6 data points again. I'm giving you the diameter of 6 circles, and you have to count how many pennies are in each circle. And then you also need to know what? You need to know the diameter of the large circle. So there's many approaches here. A very hands-on teacher who has a block period might give out this, hand out rulers and pennies, and then kids will collect the data themselves. And then they will only need to know that the big circle is 22 inches in diameter. Teacher with a shorter 42-minute period might just give out this, where ready, you have the diameters, and the kids have to count the number of pennies in each circle, and then they can go and do their authentic mathematical modeling. I'm going to come out again. I already have it set up here. Here is the data. The 1-inch circle diameter had 1 penny. The 2-inch circle had 5 pennies, and so on down to the 6-inch circle, which had 52 pennies. And you see the data here. Does it look linear? Maybe. Some people say linear. Some people say exponential. Some people say different kind of functions here. And that's why this is pretty much an Algebra 2 problem. Let's just assume linear first. Of course, my first guess is always y equals x. Not too good. So let's do y equals a little steeper. 5x, not bad. 6x, ooh, 7, 8. Ooh, 8 some people like 7.5. And they start playing around with this. Again, you're assuming linearity here. If you assume linearity here, and you think y equals 8x, then we should really use function notation. We should really use f of x equals 8x, because then we can solve for f of 22 quickly. We can find out when the circle has a 22-inch diameter, you will get 176. So if you assume linearity, the answer is 176, which seems pretty low. So probably the assumption of linearity is not correct. So we make another assumption. And most kids then move to the assumption that it's exponential, something like maybe 2 to the x. And wow, that actually looks amazing, 2 to the x. Looks like it actually fits it perfectly. So we're excited, we think it's exponential, so we do f of 22. And now we see that we get 4,194,304 pennies. And now we're not as excited because that can't possibly be the correct answer. Not linear, probably too low. Not exponential, way too large. What could it be? Well, hopefully in Algebra 2, another kind of function is obviously study a quadratic. And let's look at x squared. And I kind of like to put a constraint on that. I kind of only like to see when x squared is positive. I hate seeing the other side of it. And maybe 2x squared, or maybe 1.5. Oh, I like 1.5x squared. And then what about f of 22? Oops, 726 pennies. Wow. That seemed to be not too much off. Remember, Tanya's guess was 2,000, a lot bigger. But are we happy with 726 maybe as the answer? Are we happy that the quadratic fits this the best? Not the linear, not the exponential. Kids talk about this. Kids debate it. Some kids run a quadratic regression. Some kids play with ax squared plus bx plus c. They play with b and c terms. And we have a lot of great mathematical modeling going on. And then finally, we come back and we see how many pennies it actually took Dan. Our quadratic model, 1.5x squared, turned out to be about 700 something. Not bad at all. The actual answer is 663. We talk about error. We go back and maybe look at ax squared plus bx plus c instead of just ax squared. We talk about, again, why that linear model is way too little, why that exponential model is way too large. And we are really looking at authentic mathematical modeling here. And by the way, on this particular problem, I once had a kid do it with no mathematical modeling, but with proportion. And I don't mind that at all. Let me show you a proportionality method. So this particular student said the 5-inch diameter has 35 pennies from the handout. found the area of a 5-inch circle, radius 2.5. Divided that by the number of pennies, or pennies divided by area. So we found the density was about 1.78 pennies per square inch. For a 22-inch diameter, that's the area, radius of 11, and you multiply that by the density, and you get 678, which is really close to the actual answer using this proportionality or density method. And I'm fascinated by alternative approaches that kids may use, and we should embrace those. So finally, in summary, Act 1 of mathematical modeling, authentic mathematical modeling, is a hook. It's defining the problem and having kids really invest by making a guess. Okay? And then I'm going to stop that video. I can't stop it, actually. So you're just going to see this one play out. This is one I wrote. And I think you know the question already. What's the question? How much water did that boy waste compared to the girl? So what are the data? What's the variables needed in Act 2? And in Act 3, how do we check it? How do we talk about error? How do we reflect back upon our mathematical modeling process? So one quick commercial. In the new Envisions, Algebra, Geometry, and Algebra 2, we do have one 3-act lesson per every single topic in all 3 books. I collaborated with Dan to write all of these, so we have about 10 to 12 per book, about over 30 of them all together, and I'm real excited to have these now in our new materials. I have about 10 minutes left. I always like to leave about 10 minutes for questions. So there, if you have questions, you don't want to do them on here, you can always email me, check out my website, or find me on Twitter. So if you want to type in a question into the chat, Tanya can relay it to me. I'll be glad to answer questions right now.
Thank you, Dr. Milos. Yes,
Tanya,
please, if you have any questions, please go ahead and go to your GoToWebinar control panel on the right-hand side of your screen and go ahead and push them in just like you were doing your answers.
and again, I can't see them, so Tanya will have to relay them to me.
Okay, Dr. Milo, we do have one. This question states, do you have any advice to teachers who are starting to implement a more structured approach to mathematical modeling?
So the word structure kind of confuses me because I'm not sure what structure you're looking at. So I've defined a structure in 3 acts here. So I would kind of need to know more of what different structure you're looking for. I like to keep it more open as the structure we have here. Always willing to embrace alternative structures, but I'm not sure what it means to have more structure. It's kind of vague to me. I'm sorry I can't directly answer that. It might be something you want to email me directly, and I'll be glad to answer it that way.
Okay, one other one. This one is, will you be at NCSM or NCTM this year?
Of course, I'll be at both. NCSM breakfast. Pearson is sponsoring the NCSM breakfast, and I'll be giving the breakfast keynote address. I think that's on Monday. I don't know, Tanya, do you know
I
that?
don't. No, that's a good question. If you need that information, please chat that in as well, and we can follow up with that. Is there any other questions anybody'd like to ask? Any final thoughts? One last statement it looks like too is just a statement, not a question. It looks approachable.
Great.
And one other question is what resources is offered for struggling students?
Yeah, it's always a good, really good question. I mean, so it's in Act Two where the struggle occurs a lot of the times when you're trying to define variables and define the model. And there's where we really have to think about what resources kids should have available to them. I'm very open that they should have technology available to them to be able to Google formulas. They should have calculators available to them. They shouldn't be plotting the graph by hand. They should be using technology to do that. And at times, when kids are on the wrong path and saying variables that are irrelevant, we kind of do have to step in and have a discussion. If you go back to the water tank problem, the kids are arguing about things like the valve. We have to have a discussion, guys, is that a variable that's really, really important? And draw kids back into a conversation about what the important variables are. It's always a touchy thing, and it's really a thing about giving kids some productive struggle that we talk about in the Common Core also, but not letting productive struggle be frustration. And there's a fine line there. And I think we really have to watch the difference between struggle and frustration, not just in problem solving, folks, but in everything we talk about in math class.
Great. Is there any other questions that you'd like to chat in? Is there a demo offered for the new material? So yeah, so I can answer that one. Yes, there
Okay.
is. And I will get back with you. I will email you directly. Great question. Thank you for asking that. Yes, absolutely. Okay. Well, Dr. Milo, I think that, we got another one. Yes, I can. So that was another question that just came in to me. I will email some demo information to you all. Great question. Any other
It's a real
questions?
exciting project. It's a real exciting project to be part of, and I thank Pearson and I thank all of you for your time today. We're going to give you back 9 minutes of your time, though.
So thank you, Dr. Milo. And I'm going to, obviously, for the attendees on the line, yes, I will be in contact with you about how it is that we can get you access to some demo, or if there's samples that you're looking for, absolutely, I'll be in contact. Additionally, you have Dr. Milo's information right there. So if there's anything further that maybe you were just a little shy, didn't want to ask your question out loud, that's absolutely fine. Feel free to reach out. And I guess in closing, I also want to thank Dr. Milo. Thank you for your time and your expertise, with showing us this great resource and valuable information. So thank you very much. We do have one other webinar coming up at 7 Eastern. So it's the same. So if you've got colleagues that missed this one and you want to let them know that they can drop on in at 7 o'clock Eastern. So thank you again, everybody, for your time this evening. We'll be in touch. And thank you, Dr. Milo. We'll be seeing you again shortly here.
All right, thanks, Tanya. Bye bye, everyone.
Bye, everybody.